Yes.
My screen?
Yes, we can.
Okay. All right. So hi, everyone. Let me start, first of all, by thanking the organizers of this workshop for arranging it first, and then for giving me the opportunity to present the results of this recent research, which basically where we studied the role of quantum coherences in quasi-static quantum Landau erasure. And I want to say that, I mean, many people have already touched upon Landauer's principle. Paul Riches this morning had a very nice talk about it. And also, I mean, this will very closely connects and exploits many notions of geometry of quantum state and thermodynamics that Marty will talk about in more detail tomorrow in his lecture. But, okay, so as for this particular research, you can find all the technical details as well as many additional interesting aspects of the results I'm going to present, which of course I won't be able to cover all of them in this brief talk in our paper that you can find here, and that I strongly invite you to read if you like the topic. So let me start by giving a brief introduction, a crash course on the basic notions and ideas behind Landauer's principle. So first of all, okay, what is it? I mean, I'm more than sure that you all know about it, but okay, let me spend a couple of words just to set the scene. So in order to, let's consider a system, i.e. a collection of information-bearing degrees of freedom that interacts with a thermal bath at a temperature T. Okay, and because of this interaction, both the energy and the entropy of the system and the bath will undergo a change during the coupled evolution. And Landauer's principle connects basically the change in the phenomenon entropy of the system with the average change in the energy of the bath, which represents commonly the heat. And in particular, this relation states that any change in the information of the system is inevitably accompanied by an amount of heat which is lower bounded by kBT delta S. And when brought down to its essential, well, the most fundamental and trivial operation that one can do in this regard is the erasure of one single qubit, okay? So the transformation, let's say, from a maximally mixed state into one of the pure states, which, I mean, for convenience can be considered to be the ground state projector. And a simple calculation of the Landauer's principle shows that that reduces to Q being greater or equal than kBT log 2. And which is also the fundamental value also known as Landauer's bound or Landauer limit. And physically, this inequality means that in order, I mean, for one to erase one single bit of information, then one has to dissipate at least kBT log 2 of heat into the environment, okay? And the difference between the heat and Landauer's bound is basically a reformulation of the second law, and this quantity is also called entropy production or dissipated heat. Okay, and more importantly, the equality of this inequality is actually, I mean, this inequality is saturated when the Landauer's erasure is performed adiabatically, so infinitely slow. Okay. Well, I mean, in reality, the situation is, of course, much more complicated and rich than this toy model. And since, of course, any implementation of Landauer's erasure protocol takes place under non-equilibrium conditions, and the system is manipulated at infinite time while being in contact with a thermal reservoir, okay? So, but what I just said is precisely the playground of stochastic thermodynamics, as we all know. And in stochastic thermodynamics, all quantities such as thermodynamic quantities such as heat, work, etc., become random variables distributed, of course, according to some probability distribution. Okay. Most importantly, I mean, crucially, the fluctuations of these quantities become extremely important, and at variance with what happens at the macroscopic scale, where these fluctuations get tamed by the law of large numbers. This fluctuation become extremely relevant at the nanoscale. Okay. And while by looking back at Landauer's principle I just showed you, it's clear that it puts a bound on the average dissipated heat. Its fluctuation implies that in some instances, one could either violate the Landauer's bound or dissipate much more than its average, predicted average, okay? So it's thus extremely important, as we all know, to have precise estimates and quantify precisely how these fluctuations affect the result, okay? And let me conclude this introduction by spending a couple of words on motivating why Landauer's principle is such a milestone concept. So first of all, Landauer's principle is of course paramount importance since it represents, as we all know, the keystone between connecting thermodynamics and information theory, as Nelly brilliantly expressed in her talk before. And furthermore, Landauer bound has also become a milestone due to technological reasons. And as also Paul said this morning, this is due to the fact that all computation that's done nowadays requires information erasure because it's based on a reversible computation paradigm. And as a disclaimer, I mean, modern silicon-based transistors are still far from reaching Landauer's bound because they still waste 3 orders of magnitude more heat. But it's estimated that the miniaturization march will basically bring technology to encroach this limit upon around 2-3 decades from now, provided Moore's law is respected. But anyway, like Landauer's bound, however, has been already experimentally reached and observed in several state-of-the-art experiments performed on single particles, and which is pretty remarkable if you think about it. And just to mention one here, of course, because of the lack of time, in this paper here, they consider the following. So they consider an overdamped colloidal particle, here in red, which was a silicon bead, if I'm not mistaken, which was confined in double well potential, which this represented a generic 1-bit memory. In particular, if the particle was on the left well, then it was interpreted as a logical 0, while if it was on the right well, it was interpreted as a logical 1. And the memory erasure basically was the process that brought a max entropy initial state, i.e. a situation where the particle was half and half in both wells, was reset to one of the 2 wells, okay? And the result they obtain, which can be encompassed in these 2 plots here, shows two important features that I want to highlight here. First of all, the average dissipated heat, shown here as a function of the protocol time tau, shows that the average dissipated heat approaches Landauer's limit, which is this dashed line in the limit of infinitely slow erasure. And second of all, for any finite time, they found that the probability distribution for the dissipated heat, by the way, the dissipated heat is the same as the entropy production in my talk. I was saying that the probability distribution for the dissipated heat is a Gaussian distribution, okay? And this is important because as a consequence of that, only the first 2 cumulants, i.e. the average and the variance, are non-zero for this stochastic variable. And the probability that a single realization, a single instance of this experiment will dissipate drastically more than the average, say, I don't know, more than 10 times the standard deviation, was basically almost negligible, okay? And this, of course, is a very important thing that is taken widely into account in the manufacturing process of chips when it comes down to heat management, okay? But is this the end of the story? Well, the answer we provided in our work was no, actually, because in our research, we found that a genuine quantum erasure protocol, I'm going to define more precisely in a second what that is, but maybe basically is one that generates quantum coherence during its implementation, will result into a non-Gaussian distribution for the dissipated heat within the slow driving regime. Okay, and this has severe consequences. But let me give you a few more details and the remaining minutes I have. So the framework I'm going to consider is Landauer's erasure of a single D-level system, QDIT, realized through Landauer's erasure is realized through the change of a control Hamiltonian in a finite time interval tau, okay? And we will furthermore assume that the dynamics of the system is described in terms of Lindblad-Master equation that satisfies detailed balance condition, okay? And this last required in particular implies that for any time t, there is the dynamics as an instantaneous fixed point, which is of a thermal state, a thermal solution, okay? And in particular, this transformation the Landauer erasure is effectively realized by taking basically the spectrum of the Hamiltonian to move from an almost degenerate spectrum at the initial time to compare to the, when I say that, like the spectrum is very small compared to the thermal excitation, to a very large and very gapped spectrum. And this is like basically you can see why this is a Landau erasure implementation, because if you consider this thing, basically it means that the initial and final point represented by the instantaneous thermal points are that for the general case, basically the thermal state is proportional to the identity, to the maximally mixed state, while the final point is the ground state. So you realize the transformation from the maximally mixed to the ground state. Okay, and finally, since we want to investigate how quantum coherence, what the role is of quantum coherence generated through the both protocol, how these affect the attainability of Landauer bound, we will furthermore restrict to the slow driving regime, which classically leads to the saturation of Landauer's bound. Okay, as I showed you in the experiment before, and this is mathematically well known, and it's done by requesting that the state at any generic time t is basically a linear perturbation distant from this thermal solution, and physically means that the state always remains close to the instantaneous equilibrium state at all times. Okay. And the dissipated heat here, as we all know, is notoriously does not correspond to any observable, and it's usually defined as the change in the bath energy. And therefore, I mean, the outcomes are stochastic variables whose statistics can be reconstructed through its Kimeland generating function, for example, simply by differentiation over the parameter u. And this Kimeland generating function, I mean, can be equivalently obtained in this framework either through the familiar two-point measurement approach, or equivalently by means of the unraveling of the Lindblad-Master equation, because we assume that holds in terms of the quantum trajectories. Okay. Okay, now that I laid out all the requirement and the framework and the necessary ingredients, let me come to the results, the actual result of what we found. So the first main result of our work was to show that within the slow driving regime, i.e. Up to second order in the driving protocol speed, the Kimeland generating function for the entropy production for the dissipated heat can be split actually into the sum of two very distinct terms. Okay, the first one is a classical contribution, while the second one is a purely quantum one. Okay, and I want to point your attention to this result because it's actually a generalization of basically the splitting of the average entropy production into a classical, i.e. diagonal part, and a quantum, i.e. coherent contribution that was found like a few years ago by Gabriel Landi, Mauro Paternostro, and Gianluca Francica and John Gould in two separate papers. And this is its generalization, which is valid to any statistical cumulant, okay, to any order, which is pretty remarkable, okay. And also, more importantly, I mean, this result expresses, reflects the two different ways that a quantum system can be actually driven in the quantum case. Okay, in particular, okay, the first method, I mean, the first protocol only acts on the energy eigenvalues, okay, of the Hamiltonian, while keeping the energy eigenbasis unchanged. So it will be some protocol like this, okay, where the spectrum of the Hamiltonian is, I don't know, it's changed in time during the transformation, but the energy eigenbasis will stay constant, so that the Hamiltonian commutes with itself at all times. Okay, and this process is diagonal in the energy eigenbasis, and therefore it can be mapped into a classical evolution. Okay. On the other hand, in the quantum case, one can consider instead to change in time the eigenbasis of the Hamiltonian while leaving the spectrum unchanged. Okay, this is going to of course does not have a classical counterpart, and it corresponds to purely coherent rotation, purely coherent evolution. Okay. And okay, you can see that, I mean, in this case, the Hamiltonian does not commute with its time derivative with itself at different times. And I mean, and this leads to the so-called quantum friction, or the generation of quantum coherences through the process. Okay. And more technically, okay, this is the expression that has the diagonal classical part for the Kimeland generating function. Where you can recognize that basically here appears the so-called relative entropy between the one alpha Rényi divergence, to connect back to the several talks that of Nelly and Paul Skripczyk, for example, the relative entropy between this state and the instantaneous fixed point thermal state, and this state is the phased state onto the energy eigenbasis, the instantaneous. So it's basically rho of t after you kill all the coherences in the instantaneous energy basis. And physically, this these terms arises when the measures how distant are the system population, how they deviate from the instantaneous Boltzmann distribution. Okay. More importantly, it's important to see that, to notice that this function is quadratic in the variable u, which is the counting field u, and therefore the probability distribution for this, let's call it classical contribution to of the dissipated heat is going to be a Gaussian, because it corresponds to the Fourier transform of a quadratic function. Okay, and therefore one can see that from this result one can obtain back the Gaussian distribution that was observed in the classical experiment that was done and that I presented you before. Instead, here's the expression, a little bit more cumbersome expression for the quantum contribution of the cumulant generating function. And here you can see that, as Nelly said, I mean, one of the main quantities that also appear in this context is alpha Rényi divergence. This is the parameter of the alpha Rényi divergence. And okay, I mean, it's important to know that this term vanishes if and only if the protocol commute is a classical one. So basically, if and only if the Hamiltonian commutes with itself at all times. So we are back to the classical protocol. And also, quite remarkably, it can be shown that by purely geometric arguments, one can prove that all the cumulants, that all the statistical cumulants that one can derive by differentiating of this quantum contribution are non-negative, okay? And this has remarkable consequences for the dissipation in this quantum Landau erasure protocol. So first of all, since the quantum contribution to the average is non-negative for what we just said, then it means that the coherence generated this way always add to the dissipated heat lead to more dissipated heat on average to the erasure protocol. And more importantly, since they also lead to higher fluctuation, to a positive skewness, a positive kurtosis, and so on and so forth. And this basically marks a neat departure from Gaussianity of the dissipated heat distribution. And let me conclude, if I have a few more minutes, by showing an important, the application that we studied of the above results. On this very simple toy model. It was basically the Landau erasure of a two-level system whose Hamiltonian is given here in this form, okay? And the assumptions are those which I described at the beginning. So Lindblad master equation, detailed balance and slow driving. And the erasure protocol is realized here by taking epsilon 0, this epsilon of t, such that epsilon 0, the initial value, and epsilon tau, the final value, to be much smaller and much greater than kBt respectively. And you can see that the mixing angle theta of t encapsulate the competition between the energetic bias sigma z and the coherent tunneling between the two states sigma x. And whenever you don't change this theta of t in time, basically then you're back with a classical protocol. While if you change theta of t in time, then the Hamiltonian will not commute with itself at all times. The energy eigenbasis will rotate, and therefore you're gonna see this quantum contributions. Okay. So in particular, analytical results can be derived for all the quantities that I've shown you before, but I'm not showing them because they are, I mean, the expression is quite cumbersome, but let me show you the results. Okay, this, by the way, okay, these are like the various results. So you can see this is the value for the average dissipated heat. And as you can see here, I mean, the average is not greatly affected by the presence of quantum coherences. In all the plots that I'm showing you, like now and in the more slides, the dashed line corresponds to the classical protocol where theta is equal to 0 and not changed, while the solid line corresponds to the case where you also change in time the angle theta according to this protocol. Okay, this is the actual protocol that we implemented. So the average is not greatly affected by the presence of coherences. They lead to a positive contribution, but it's almost negligible for almost all temperatures. But okay, some big difference can be seen at the level of the Fano factor. So like the second moment. As you can see here, I mean, like the Fano factor is equal to 2 for any temperature. In the classical case, while it deviates for I mean, this quantum correction acts as a deviation of the fluctuation dissipation theorem in the classical, in the quantum case. And so therefore means that this quantum coherences represents this kind of corrective term to the quantum fluctuation dissipation relation. And I believe Marty will tell much more about this in more detail tomorrow. And finally, you can see here that the third moment and the fourth moment, which are the skewness and the kurtosis. I don't know what the other moments, higher moments are. Probably the co-kurtosis is the fifth one, but I don't know. So they are 0 in the classical case, as you see from the dashed line, and they become positive quantities for like as soon as you ramp down the temperature, so increasing beta, these become more and more relevant. And actually, if you perform a quantum jump trajectory interpretation of this protocol, you can get a very nice physical and clear physical insight of this positive skewness and kurtosis. And I wanna briefly tell you about this. So if you imagine to start with a pure state with some pure state psi, okay, and interpret the evolution in terms of these quantum jump trajectories, this is basically what happens. Okay, you have after some time t1, basically some jump takes place, and basically the excitation, this brings the qubit to its ground state, and this is accompanied by an emission of an energy h bar epsilon t1. Okay, and classically, this is important. Classically, this can only be followed by a subsequent absorption event. Okay, and so on and so forth. In the end, essentially, this is basically the histogram that one recovers of the energy. Okay, so any emission event is followed by an absorption event, such that the sum of these, the stroboscopic sum of these, almost cancels out, and as a result, the total net dissipated heat, which are going to be quite small and near to the Landauer's bound. But what actually happens in the quantum cases is what follows, and this really makes clear the picture why they cannot have a classical counterpart. And because of the fact that, let's say, after an emission or an absorption event, the actual energy eigenbasis can rotate, okay, then there's basically there's a probability the state will find itself in a superposition of 0 and 1 after some time, and therefore I'm going to have a certain probability to have another emission, like to subsequent emission after some certain time. So this corresponds to these events. Okay, so 2 subsequent emissions. And let me just say that if you're wondering why I almost never observe 2 consecutive absorptions, this is because the detail of the detailed balance conditions. Okay, which of course exponentially weight more the probability of emitting than absorbing. Okay, and as you can see here, this is the result of quantum trajectory simulation ab initio of that protocol, which basically show that while the bulk, as you can see, the bulk of trajectory is essentially Gaussian, 1 out of 10,000 trajectories will show extreme dissipation. One example of such statistical outliers is shown here, where basically the dissipated heat we found was almost around 30 times bigger than the average of Landauer's bound. Okay, and let me say that like 1 out of 10,000 trajectories is a rare event, which is reflected in the skewness, and not in the average. But it's not that rare. It has it's a pretty big number actually. So in conclusion, our study illustrates that quantum coherence drastically increased the likelihood of extreme heat fluctuation event during the process of information erasure, of this quantum information erasure. And such event could potentially damage or disrupt small-scale quantum hardware, and which are built with a low threshold of tolerance for heat dissipation. And therefore, this work highlights that these statistical outliers may have severe consequences for nanoscale heat management. Thank you all for the attention.